Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
Now that we've talked about rigid body kinematics, it's time to move on to the next step, which is rigid body kinetics. The start of this is to have a review of moments and moments of inertia. Now, the key equation that we use for rigid body kinetics is that the sum of the moments is equal to the moment of inertia matrix multiplied by the angular acceleration vector. Now, the full 3D form of this is pretty tricky because we have this 3x3 matrix to deal with. And essentially what this means is that it's easier sometimes to spin things in one direction than it is another. For instance, if you have this pin right here, it's much easier to spin it about its axis than it is to spin it around. So in general, we need a full 3x3 matrix in order to describe how the moments interact with the angular acceleration. However, if we restrict ourselves to rotation in 2D, then we can only rotate in one direction. We only have one axis of rotation. That means that we can get rid of two of the components of our acceleration and deal only with rotation about the k-axis, or the axis coming out of the board. I can write this as sum of the moments, and since I've gotten rid of the I and j components, I only have the k components left. And this means that I have a scalar valued I multiplied by a scalar alpha, which again is multiplied by this k unit vector. And when we're doing this, we generally just leave off the k term and think of all these things as scalars. So kinematics has already talked about what's going on with this alpha. What does alpha mean? What is it doing? How do we deal with it? What we need to do now is talk about the moments and the moment of inertia. Now, this is typically covered in physics, but I'm going to try and do a quick review right now. So the simplest way to write the moment is just the force multiplied by the moment arm. And to be specific, this moment arm d is a distance that is perpendicular to the line of action of the force. So what do I mean by that? Let's say we have a system here composed of a cylinder that is pinned to our center. So it's not moving anywhere, but it's allowed to rotate. And we have some lever or arm that's connected to this. And we're applying a force in some random direction. So this force has a magnitude F. So we can find out what D is by just drawing a line right along F. So this is what we call the line of action of F. And the distance D is this distance here that is perpendicular to that line of action and runs through the point which we're measuring about. So this distance here is D. And so our moment is simply F multiplied by D, as we wrote before. And in this case, it's positive because it's causing some positive moment about our origin point here. We need to know some of the geometry of the problem in order to do this. So if we drew this out further, we could say that we have some theta here, which defines how this triangle is built. If we have some distance r, then in this case, d is equal to r multiplied by the sine, because we need the opposite of theta. Now, if instead of the geometry, we actually just know the two vectors, so if we had two vectors, and this works for 3D as well, we could write the moment as r crossed with f. And if you remember vector arithmetic, this would be equal to I, j, k, then we'd have r in the x direction, r in the y direction, r in the z direction, and then the f's as well. And you would take the determinant of this little matrix in order to figure out what the moment was. Now, we said that we're really only interested in the 2D problem, which means that we can get rid of the z terms. Now, if we do that and take the determinant, we end up with Rx multiplied by Fy minus Ry multiplied by Fx, and all of that is multiplied by this k. And which of these formulas you decide to use would depend greatly on what information exactly you're given. If you're given an angle theta, then it might make more sense just to use the definition of d here and plug that into the moment is equal to f times d. If you're ever in 3 dimensions, then it becomes very difficult to use something like this, and it usually makes sense to go ahead and use the full cross product form. Or if you're just given a I and j components for each of these, then you should just use the cross product form. So we're going to assume now that we've found our moments. In order to get our alpha term, the angular acceleration, we still need to know what our moment of inertia is. So just like mass is kind of the resistance of an object to linear movement, the moment of inertia is the resistance of an object to angular movement. If the moment of inertia is higher, that means that you need more moment in order to give it the same angular acceleration. So the definition of the moment of inertia is simply the integral of r squared times dm. To be specific, this r is the distance from the axis that we're rotating around. So we can extend this to any of the 3 dimensions. But for now, we're just interested in getting this about the z-axis, which is this k term that we're rotating around. So let's do an example problem and kind of work through the math. If we think of a cylinder, we can find a dm element. This is a differential mass element. So in order to get that, we need to just cut out a little section of this cylinder for us to find a mass. The mass, this differential mass, is simply equal to the density multiplied by the volume that this is taking up. And the volume of a little rectangular prism is simply the multiplication of the 3 lengths that it has. This length here would be the length in radius from the center point. The height of this thing would be a dz, and then the width that we see here is the radius multiplied by d theta. So our d vol can be split up into rd theta multiplied by dr dz. So dm is going to be equal to rho multiplied by all that. So the moment of inertia of this cylinder is going to be the integral over the entire cylinder's body. So we need some information about the height of this thing. We need some information about its radius. So we can integrate over the height, and this is going to be in the dz direction, so we get one of these. We integrate over the angle, the d theta, that goes from 0 to 2 pi. And then finally, we integrate in r. So this is from 0 to this capital R. That's in the dr direction. And we need the r squared here, we need the rho over here, and we need this final r. So we'll end up with rho r cubed. Now we can split this into its pieces. For this problem, I'm going to assume that rho is constant, that we have constant density. It's the same material throughout. So rho is going to go to the outside. We're not going to worry about it. Then we can have the integral from 0 to h times dz, the integral from 0 to 2 pi times d theta, and then finally the integral from 0 to r of r cubed dr. So now we can simplify, and we end up with the moment of inertia of a cylinder being rho times h times 2 pi multiplied by this last term, which becomes capital R to the 4th divided by 4. So I'm going to write that a little bit cleaner and end up with just pi times rho times h multiplied by r to the 4th over 2. So we have a moment of inertia, but it makes a lot more sense to write this in terms of the mass. Usually we're not given the density and the dimensions of an object. We're told what the mass is. And in order to get to the moment of inertia, we really want a simpler formula that includes the mass. So the mass of the cylinder is a very similar equation as to what we have above. But instead of integrating r squared dm, we just get to integrate dm. So then we can write the extents of that using this form of dm over here and just copy basically all this down except for that extra r squared. And we can split this up as before. Essentially, the only thing that changes is the r term. And so we end up with rho times h times 2 pi multiplied not by r to the fourth divided by 4, but just r squared over 2. So again, simplifying, this becomes pi rho h multiplied by r squared. So now we can find the moment of inertia in terms of this mass. And that's just equal to this 1/2 term times all the rest, this mass of the cylinder, then finally multiplied by the extra 2 r's that we have. And this is the form that you'll usually see for most normal objects. So we can also write the moment of inertia of a sphere, which is equal to 2/5 times the mass of the sphere multiplied by the radius of the sphere squared. And if we had some ring, then this would simply be equal to the mass of the ring multiplied by r squared. And the reason for this, of course, is because all the ring's mass is concentrated at exactly r away. So r is a constant here. We can just integrate with respect to the mass and find mass, and so we just have mr squared. And the last one that we'll be using a lot is the moment of inertia of a rod. And this is equal to 1/12 times the mass of the rod times the length of the rod squared. Now, all of these are about the center of mass of the objects. So if we're rotating about someplace other than the center of mass, then we need to use the parallel axis theorem. Also, these are for some very specific objects. If we're talking about other objects, then we usually talk about a radius of gyration. So these are some other terms that you may hear, but we will get to those in a separate lesson.